Thank you, Bastian, for the invitation. And thank you also, Nilay. I don't know if you are around. We had a couple of discussions during the EU last year, and that motivate me to make this presentation. So that's kind of compiling talks with experience from previous years, and the idea that there is maybe some sort of boom on the use of machine learning, and there are many uh, issues that uh, will appear when someone is reviewing the papers, or when someone is maybe entering into a phase of trying to use your model, or use the model, or understand what is the final applicability. So I compiled many things here, and the main core of the project is, or this work is to try to raise the idea of that there are many physical elements on the machine learning model that when you use it for hydrological purposes, you will be uh, yeah, able to take advantage of them, or vice versa. You might making some mistake, or generating a discussion around what did you do and why did you do it. So the first thing is, in the last years, we have seen an exponential increase on the use of machine learning and AI titles in almost all the sessions of the EGU. And I did some uh, word cloud on the lower side of the screen, that you can see that machine learning appear on almost the sessions of all hydrology. You see the word is one of the most prominent. This word cloud highlights, gives a weight to the word that appears most time in the session. So this was just extracting all the words from all the abstracts from all the sessions in hydrology, And there was also during these sessions the questioning from some of the professors, saying that there were many people doing models using machine learning, but it was in many of those presentations the the why, what was the reason they were doing a model. It seems many of the models were generated with some elements that were not clear if the model at the end will be of any use. The other one was, how comes that the model works if there is no physics behind it? So there are some uh, work done that we noticed that some variables were used, but there are no physical reasoning behind the use of those variables in the explanation of the phenomena that they wanted to reproduce. Where maybe what is logic and what is not on building a model, and if it's a black box model, when we call these machine learning models, uh, why you want to explain it. So at the end, you're building something to be able to do something. So the question is, how do you want to explain it? And this is more a computer science question. In physics and in hydrology, we always want to explain everything. So that's an important point. So this presentation, then I will cover a bit on, or discuss on this, and giving some examples and going through some techniques of explainable AI, but as well maybe trying to reach the moment where I will elaborate on these things that we are talking about, the model. The first thing, so where does this machine learning come from, and how this AI has been developed? My assumption is that most of you, or the ones that are in this presentation, know a little bit about machine learning, how to build a model, or at least have built a model one time, know about some of the algorithms. And many things that I'm going to show here will go on the assumption that when I talk about maybe a general machine learning model, I will be talking about an artificial neural network. Doesn't matter if it's a MLP or it's an LSTM. Or in general, just trying to talk about systems that has nodes and has layers and have these training processes, or at least In 90% of the presentation, I will try to mention it like that. Now, the traditional approach in computer science is that this came as of course artificial intelligence 1957. The concept started to grow, and the idea was, okay, we need to something that will reproduce the human brain, or at least reach a level of intelligence that can be mimic, even in quotation says, like an animal. And that's, yeah, 57, 1957. Of course, it develops such that in one moment this was more about automation. How can I make everything automatic, process everything very efficient? And the way that we used to do it, the first thing was traditional programming. So you had some data, you make some analysis of that data. For example, you need to build a river model, a hydrological model. What do? You try to find equations and see how the process goes, how these equations interact, and then you create a program which you use. If this happens, then that happens, and then I have to go 10 times because I have 10 elements analyzing if, then, and so on. And then you create your program, and then you have your output. That's the main idea on programming. But the idea of machine learning will say, okay, let's replace those programs, and no, not anymore. We don't want to have the task to go in so many details. What if I already know the output that I want to obtain? For example, if I want to make a lift to go up and down, or a control system in a reservoir to operate based on certain level, or any type of automation, you already know what are, in principle, what are the outputs that you want when certain input comes. So if you know that the input is X and the output is Y, then you would like something, some machine learning that will be able to represent such input-output data. And then what it comes out of this is that you have already the program. So not anymore make the program yourself with all these if-then rules, but you are able to reproduce anything. So a hydrological model, like inputs, outputs, rainfall runoff model, but also you can talk about a robot, a car driving, anything. So that's mainly the key on this message. Why is different for what you will see in the paper publications, or on most of the journals? When we are talking about science, we really want to understand the systems. And if it's a black box, of course, we will not be able to understand too much from the black box itself. However, we can reproduce as much as we can the system. And if we look into this graph on the right, on the left side, you will see that most of the time we have measurements of a natural system. We have the knowledge of the system. We have the physics, how social science, ecosystems work. And from this, we can get attributes and measurements. And what we want to see is how these measurements and this understanding of what we relate as input outputs in our systems can be reproduced and can allow us to understand more the system. So we do a data analysis, or we make a supervised or unsupervised learning. So we make machine learning models, and we obtain predictions, or try to understand a bit more what are these relations, how can we predict information that will happen later, knowing what we know now, or maybe through, as I was mentioning, clustering data, we could group the data and understand the patterns in those data, and with that come with new discoveries, and then try to improve our knowledge and our measurements of the system. So this, as you can see, this is different if you are going to go to present a research in a journal that is related more to hydrology or physical science. uh, Having a paper that will tell you that you managed to map input with output data, well, it doesn't have uh, too much gain. You are just telling us that you were able to, like, build a regression model, simply like that. So therefore, the challenge is understanding or solving a real life problem. So we need to balance in one part, there will be a challenge for sure. You will need to reproduce what you see here, the model reproduction. So how can the model reproduce the real phenomena? But that will not be the core, is one of the challenges of your research. The other one is understand are you, what this model is telling you, and so you go discovering patterns, and after you discover patterns, then you have this advancement, how these patterns or how the understanding of what you manage to get from the model is telling you something. If you have these three things in a paper, probably you are quite there for showing your work. But what most of the time happen is that you have, this is the way that we learn, we make the machine learning learn, and is that we collect our data, we do our pre-processing. You can outliers, remove outliers, fill in gaps, make the normalization, make even sometimes transformations, then make a future engineering to detect what are the most appropriate variables, your model selection, then your training, then the evaluation, and then finally send it for production. Um, but this standard seems to have something that is missing, and that's what I want to elaborate on the following the slide. So it seems that if you follow this, you can do it with almost anything. And in fact, this is in the presentations that you will see from Microsoft, from IBM, from almost any computer science uh, uh, website or whatever. You will see that this is the standard procedure. However, there is little emphasis on the why and what of the model. That's a key variable that is missing in most of these diagrams. So how does the normal or the automatic way to generate the models work? And as I say, my assumption is that you have done some modeling in the past, and therefore this diagram is maybe quite familiar. So the first part is you have some measurements of the system. And in hydrology, well, most of the time you have discharge, we have precipitation, we have temperature, we have other hydrological variables measured from the natural system. And the natural system is doing some things, and then you have a response. Kind of, if you want to make a simple case, it's rainfall, runoff. So if you have rainfall, what will be the discharge of the river at the end of the catchment of the basin? If you want, you measure this, but now we want to create, for example, a machine learning model that will be able to reproduce this system and tell me how much will be the runoff in certain time step. So I build a machine learning model, which in fact is simply a mathematical function. You have certain parameters and you have certain inputs. And then if you have not trained it, the inputs starts, let's assume, with a random condition. The input comes, your measured inputs, and then you obtain some output and you compare and you say, this is not right. Then what to do? Then I find a function, a target error function that will allow me to understand how far is this output with the measured response, and then having that information from the output and having the information from the parameters, initial parameters, I can start to generate new parameters that will go into the model. Then I run the model again. I have another output. I have another error, come back. And this training, what is going to is to minimize this difference. We'll start to generate parameters in such a way that this error will be reduced. So far, I think is pretty standard. But if you think into that process in a more holistic way, then we have the big challenge where everyone says, okay, building a machine model seems to be pretty straightforward. But if you look at the first step, you are analyzing your inputs. there is a high uncertainty on this analysis. What if someone did a normalization in certain way, another in another? Which one is the right variable that interprets the phenomena? Uh, that's not known. So what if I two persons or three persons selecting different variables, but it's probably yeah, not a big deal. You might get a good result even if you select one or the other. The only difference will be the model that you're building has different parameters. That's all, but probably accuracy could be very similar. The second step on your work is we are working with data, so we need to make a sampling. This sampling is normally done random, of course, keeping in mind that you need that your groups of samples should be very similar to each other. So you are not going to make a verification of your model if it works well after training it with a data set that has completely different ranges of values. So you need to have homogeneity in training and verification. But still, this is random, which means also two or three people can have different models with probably could, if they start to calibrate and do all the tricks, they can have good results, accurate results, but the parameters are different. So there is a uncertainty associated to why these two models are providing accurate results, but they are built in different way. Number three is the calibration. And calibration, as I mentioned a few minutes ago, how do you start if you are trying to generate a model that will be learning from its errors? You need to start in somewhere, so you need an initial condition. This initial condition, again, is random. So if we are 10 people building a model, we will come up with different initial condition, which imply probably my model also will have different values. Next one is random optimization. So also depends. You select one random optimization, I select another, the other one select another. We all will arrive with different results. And the last one is very interesting because the last one will relate to what are you looking for is the error measure. And one of the interesting things is here in the hydroinformatics groups, we have always uh, posed the challenge for the students to try to understand what is the difference of trying to think on using root mean square error or minuscule absolute error or using information theory as an error and so on. Every measure of error will assume that your target and your predicted values should behave in certain way because you have thousands of measurements, thousands of results of your model, and then, for example, if you want the high flows of a hydrograph to be fit, then your root mean square error will punish the difference between one and the other and will square it. If you want low flows, this will not be good because then you are punishing the high values, not the low flows. The low flows, the optimization will not care too much about them. So the point here in the number four is that you will have a lot of freedom again. You could be saying that one model is accurate with the same data set and even with the same type of modeling system. Both could be using deep learning, but if one use one error measure and the other one is another one, it might be completely different and could be both saying my model is good. This all goes into this traditional graph, and so if you Google and so on, you will find this type of joke whereby they say, okay, this is your machine learning systems. Yep, you put the data into this big pile of linear algebra, then collect the answers, and on the other side, yeah, yeah, what if the answers are wrong? Just you pile until they start to look right, and that's basically it's basically what is happening. Of course, the 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 idea of doing it in science, we want to look a little bit further. And this is implicit in many research and many publications. In fact, what has been done, but sometimes is not well explained or not well. described is that you first define the purpose of this and the context. And that means that you collect the data related to the purpose. So one time I was in a conference, I was asking everyone, what do you need to before you start the model? And someone said the data. And then I mentioned, well, before the data, you need to know why you are going to build the model. What is the purpose? What is the context? And then here you will see another thing, the representation needs. What do you really need to represent to define this purpose? Not only collecting the data, but then with that data, is that enough to represent what I want to represent from my phenomena? If I am going to do whatever I want to do, which problem I want to solve, I need to find how accurate it will be. And this sounds silly, but many models that goes into forecast, many publications you will see, and there is no any accuracy target. They just say, okay, I want just to forecast, and they compare one model to other. Some of them even don't compare one to another. They just say, I want just to forecast, and then there is no accuracy in it. It's just I am doing well when I do this, and when I do this another one, I am not doing well, and that's it. And the other one is feature engineering. There is this process of defining which variables are useful for me, for my model. I'll always a large discussion on how much the physics can influence my decision. And I will show a little bit of this in few minutes. And then the other one, the last one, let's say in theory, the last one is the model selection, to have an optimal model selection before we go into the rest of the process, no, because we will have to train and so on. But I wanted to stop here because this model selection is also another thing. Right now, I had the students last year that start to say, okay, I want to do but transformers for what? Oh no, it's transformers. The attention is all what you need. It was the idea of the large language models, and now we know that they are excellent. And that's great, in fact, to use it. And then we of course we use it and we try to develop them. But the main point of the research should never be that you just want to test the model if you do not know test it on what. There's a criticism on if you have you know the hammer, you just want to use the hammer in anything, and instead of trying to analyze what is the criteria. So, for example, what are the temporal model? So is a time series model, or is a spatial model, or is a spatial and temporal model, or it could be even an abstract model, a model that doesn't have time or space in the information, is just a bunch of data that was measurements of properties or characteristics or whatever. And therefore, the type of model is different. So from this perspective, the question is, if you are going to go into now solve a problem, the interpretability is one of these first variables that you need to look in the model, in building your model. Uh, why? Because if depending on how much this model will solve a problem, you will be requested probably to explain it. And then, so which type of model to choose based on the interpretability and the performance? So what offers the interpretation of the models, and what offers if I cannot interpret it? What if I have a very complex model? So I have these two decisions to make. If you want something that is very easy, like a linear regression that I can interpret how the parameters of the equations are giving me results on my problem, or deep learning with thousands of parameters where I have probably high performance, but it might difficult to explain it. So this is something very important. In computer science, you will find in many websites that explainability and interpretability are used interchangeably. However, when you go deep into people that are working on especially explainability and interpretability, there is one difference. The explainability, it's like looking at how can you explain the process or the results of what you are doing. So, like when this happens, what is the result? So I'm explaining the phenomena, explaining how the model responses. Interpretability goes more into how can I interpret the parameters or how I interpret the model itself. And you can say here into the model internals. So how inside the system, how the inside is working. The explainability is explaining the phenomena. It's trying to explain what I get with one or the other. So with that one, then the question is, how can I balance what type of models I should select? So one thing is I have low interpretability or high need for interpretability, and this depends on your problem. So if you need high interpretability, what can you do? So these are the boxes on the top. If you don't need high interpretability, what are your options or maybe what is available there? And on the lower side, the left side, you see low accuracy. So you need to be certain. So you here have high accuracy. You really need to know what is the precision. You need to be very accurate. And the different options are if you this is the most common element, and I added one line here, but the common elements on models that you can interpret so you can see inside whatever they have are decision trees because, well, you say if this happens, then go in one branch of the tree and so on till you reach the leaf, and then the leaf of the tree will tell you the value or a linear regression model that say what is happening. Simple linear regression models. These are generalized additive models, so one model on top of the other, rule-based models, or and this I added because we are in hydrology, so maybe a conceptual hydrological is easy for you to really understand. Sometimes, and I put it here on the left side because sometimes it have low accuracy, but is interpretable. And while it's interpretable, then maybe that is something that you might need, even if it's not so accurate. And this I have to mention, I have seen many SWOT models or many models, HMS or whatever, that are on accuracies of 0 0.5, 0 0.6. And they, they, they are quite useful. They are used to interpret phenomena, generated scenarios, and so on. However, if you run a simple machine learning model, probably you can get 0.88, 0.90, whatsoever representation, even without too much. On the right side here is one option. If you want to build a complex model, then you have to go maybe for the decision. I will go for a deep learning model, but I need to add methods like Lime and Shape. And I will chapter this without E, but I will show a little bit more about that. And other options, so like gradient boosting, and this is also one of the most I would say strong models. It is a combination of many models trees and sampling the data. But then if you do that, then you need to add something to help to understand it. So try to build feature importance analysis on top of it. Okay, but this is maybe something that I wanted to discuss this now. If you are going to go into a model, you have these decisions, but there is always the variable, the data. And here goes from the left to the right. Indeed, if you have very little data, you will see that most of the time the interpretability plays a big role there. Having let's say, a very interpretable model, physics-based, you don't need too much data. If you know the physics, you just need one parameter that says, yeah, force equal mass multiplied by acceleration. And if we are talking about throwing something, the gravity is already known, the coefficient. So your phenomena almost doesn't need calibration because the physics dominate. So low need of data means probably highly interpretability. And if you have a lot of data, yeah, then you can go for, yeah, lower interpretability, but high accuracy. Good. Now that we know the context of, let's say you guys already develop a model, already discuss all these possibilities. It's a good to go to one example of what happens sometimes, and maybe, yeah, show some remarks to say what is critical in the building of the models, and maybe make you think more deeper on your own problems. This is a forecasting model. This is the Bagmati River basin. There are many papers in this basin. The area that this basin is located between in Nepal. You see here in the center. Nepal is in between China and India. This is more or less how the land use um, is represented there. With a basin of 3,750 square kilometers. Is flow dominated by springs and smooth rainfall. So what does this mean? You have a high period of rain. So this is 3 hydrological seasons. A dry pre-monsoon business, so you don't have any water. It's very dry in the region. Then all the water comes again in June and September is highly concentrated. So you have a lot of floods in the region. And then again becomes dry. This basin, as I mentioned, have been studied quite a lot. What I'm going to just show some results of 5 years. And I did this exercise just in a very pragmatic way, whereby what you see on the upper side is a very traditional concept for a neural network. This is an MLP, a multi-layer perceptron, layers here, nodes. And what normally is done if you want to forecast discharge is that you use a little bit of the discharge on the previous time steps, which you define by correlation analysis to see how much you could go backwards on time to predict the future. But also you see how much the precipitation is correlated with your discharge, and then you add some past precipitations and inputs. And like in this example, you could have 1, 2, 3, 4, 5, 6 inputs to target your future probably discharge QT plus 1. And this is very common, most of you probably have used similar concepts, and therefore it's normally highly accurate. It's very important to know that it's a fixed time step. So in terms of physics, since the physics are not here, if you want to shift into intervals that are not here or different type of phenomena, well, it's not straightforward. And of course, there is no clear knowledge representation on this one. So the interpretation of this one, it's pretty uh, difficult. But of course, there are some studies that has done it, and I can show you also some examples of how to interpret this. But key message, artificial neural networks just jump into a forecast horizon and can give you the result in the future. Like what you see here is the rainfall runoff representation. The lower part is the discharge. As you can see, it goes up to 5,000 in an extreme event, 5,000 cubic meters per second. Precipitations go the range of 0 to 100, 150, depends on the year. And what we have is something, as I was mentioning before, QT plus 1 is equal to a function of precipitation and a parameter. So this will be mainly rainfall runoff. However, in other cases, you will see that some people add here discharge, and then, of course, then it's not anymore rainfall runoff in the sense that you are having runoff rainfall to obtain runoff. Then the other important thing is that you want to go more than one time step ahead. So you could jump 2 time steps or 3 time steps, or like what I'm showing here, you can say the QT plus 1 will be using the results of the previous one. Good. So this is the problem that we want to solve. We want to see how much is the forecast, yeah, up to 6 days, and what can the neural network provide me. And the first thing that you do in this machine learning analysis is then, okay, I will make a correlation analysis. On the left side, you see the autocorrelation function of the discharge, and it shows it would appear at the beginning is almost 90%. After 1 day, it goes into 75%. As the 2 days goes into 0.5%, so 0.5, not percent, sorry, 0.8, 0.5, and so on. So this autocorrelation function is telling us already that there is a limit on what we probably could uh, predict. So if I'm going to build a model, I might be only using one or two of these past discharge. And here, between precipitation and discharge, you will see that if this is the zero lag, and if I move on the left is 1 day before, 2 days before, 3 days before. On to the right is 1 day ahead, 2 days ahead, and so on. Symmetric. So going to the future and the past is the same in the sense of time series analysis in this case. But you can see here it goes between zero point 0.6 to 0.37 something. So as you can see, is much lower than the fourth day. So it will means that probably the autocorrelation with the discharge up to 4 days is more important than the precipitation in 1 day before. So it starts to be a little bit more, already is telling us something. And in general, we will see that it's saying kind of your rainfall phenomena is not as strong for the discharge as the natural stream, which means that this basin, and as you can imagine, is close to the Himalayas, very high. It's highly dominated by base flow. So the main stream or the main contributions are coming from deep into the mountain than the rainfall events are relatively small. But let's see what the theory tell us. So if I say 1 day and the lag of the basin is 1 day, then if I take 2 days or 3 days, there is a problem because the rainfall it's has not happened. So 3 days before, the the area that I assume that has a 1 day lag still did not receive the rainfall that will come in 2 or 3 days before. So is there any sense on me trying to use data to predict uh, a flow which has not been affected by any rain? How important it is to think about if the lag is 2 days, why I will use 5, 6, 7, 10 days of lag is nonsense. Probably will not give me any added value, right? So I have to think about has the rainfall occurred? So if happens now, what is the response? If it didn't happen, then not. Then if I want to use this as a basis for my machine learning model, I cannot go more than 1 day. However, this has been criticized by many people because in fact there's a reasoning behind. If you look deep into physics, you probably will see that the soil motion in the catchment retains a memory of the past rainfall events. So having no rain like 10 days before the rain event is information for the machine learning. It will tell me that the soil is dry, the type of response is different. He will be able to capture this this information as part of the idea that there was no information for those days, or there was no rain, or there was little rain. So if you see it from that perspective, it's not anymore the rainfall runoff, as you will see forcing and a response. It will be the system itself is embedded into the patterns that you are going to give him as input. That's one very important one. Another one, yes, last year I went to Florida and there was one forecasting um, system. One person was using deep learning, LSTM, and they said we did it great. We have one model that is being able to forecast almost one continuous year with one LSTM, something that was not ever possible before with multi-layer perceptrons and with the normal recurrent networks. But now with LSTM, we did it. And then I asked how was the structure of the model. So the model was taking 365 days on the past. Then okay, the reasoning that the rain has not happened already here, it's one important point. But in this case, now it's even worse, more than 3 months, 4 months, even almost a year. So the why it was giving so much good result. And one of the the thoughts behind it is that there is a cycle on the earth, of course, and we have our what we were seeing a few minutes ago with this case study, precisely the monsoon season, pre-monsoon season, and how this idea of having the complete 360, the complete yearly cycle in patterns that were used to train every day for more than 10 years already is giving you enough information for as soon as you train it, you can run it in 1 year or 2 years or 3 years ahead. You can continuously keep using it, and it will not give you so bad results because it's kind of mimicking year by year the behavior without caring about if there is one rain or not event or whatever. It's more or less trying to capture is more what happened in the past. This is the second point on building these models. The third one is over parameterization in LSTM. And if you are going to present a paper in LSTM, then the question is how many parameters do you have, and you will, after you finish building your model, you will notice that you have thousands of parameters. This contradicts the idea that that you should not have more parameters than data, and this ratio normally should be quite high on the side of having enough data. However, in many cases, there is a clear overparameterization. Starting from large language models, they are over-parameterized. They have hundreds of millions of parameters, and so hundreds of millions of data is almost relation one-to-one. I haven't thought into exactly how much is this availability of data, but you would imagine that it's not going to be at the ratio of the parameters that they have, and then bringing them down is a story. But the key message is keep in mind what is happening, because in physics, the people or you will get into thinking that how much every parameter represents an uncertainty. And that's a key element in this interpretability of your system. Uncertainty extrapolation. If it's a black box, you train it in one certain group of data, and then many people say, "Oh, what happened if we do not have rain, and what will be the discharge?" Well, that should not be the case, because you cannot extrapolate phenomena in the sense that it has never learned such situation where you, for example, had a rainfall that was above what you ever measured, or a value where never raining the whole year. You will get just garbage. So that will goes into garbage in, garbage out. So you try everything, but the model it has a kind of a structure that was learned with the patterns of data. So the extrapolation of that will be quite difficult. And okay, but then maybe to bring up a little bit of data into the game. This is the hydrograph of the Bagmati River Basin. Try to think about how good is this result. It's 1 day ahead, LSTM, 20 nodes, standard training, 70-30, normalization, whatsoever. It uses all the standard procedures. And as you can see, it kind of is capturing the peaks, having some sort of values. Some, as you see, the predicted is the red one, so it's overestimating in certain parts, underestimating in others. This is 1 day prediction. So, and if you looking at this graph, is not so easy to find the errors. But if we do one minus the other, here we can see the errors, and you can see that it's up to minus 1,000 cubic meter per second in certain moments, but in average, it's more or less good. If you look at that, then I want to go even further. So I start to build one for 2 days, for 3 days, for 4 days, 5 days, 6 days. So this physically, if you want to criticize the idea, there is no sense on doing more than 2 or 3 days. But look, in general, we are getting more or less good results there on this, or no, good results equivalent to the results of maybe 3 days. But it's difficult to know here what is good and what is not good. And that's what I said in the beginning. You need to think about having a reference of understanding what is acceptable. For example, this is 6 days. And in 6 days, we can see here already that it's underestimating all these peaks, but also is getting crazy behavior. And something very interesting, you never have discharge, negative discharge, and it's giving here a lot of negative values. And instead of having errors of almost up to 1,000, then it goes to 1,500, and you can see the spread on the events. And even here, some delays in the responses. So this model, yeah, seems strange, has negative discharge after 6 days, although the error seems to be more or less manageable or compared to the origin the first 2 3 days. Then if you look in detail, it's useless. But then we go even deeper, and they say we need a reference model. What for us is a good forecast? And then for you guys, probably the ones that have worked with forecasting, will know that the naive model, the naive forecast, is saying tomorrow will be the same rain as today, and that's the most easy, most stupid, most simple way to do it. And if you do that, then you get this, what I call here the naive model. So it's assuming that every time step, the next time step is the same one. It's, by the way, is very, very powerful when it's depending on certain time series, it's very difficult to beat this reference. But if while you do better than doing that, then there is an added value on using your machine learning model. So here there is an added value, here there is an added value. And as you can see, as soon as you go ahead in the future, it's reduced. Probably if I continue going, this will go 1 to 1, and in one moment the blue one will go up and the red one will remain down. That's it. But now I can see that still there is some gain, even up to 6 days. There is a good reason why to use machine learning model that have some approximation. These are the same 6 days ahead, and it's comparing again, in this case, the MLP and the naive model. And something very interesting, look at the bias here on the lower part, yeah, and how it starts to go for 0, 0, then 500, then 1,000, then here around 500, then around 500. So as you can see, the dispersion of the machine learning model at the beginning, close to this black line, you will have good values, good forecasts. Everything that starts to go side to side starts to be worst. And then here, for example, you see all the ones that were close to this have disappeared, and then it starts to be even flattener. But in one moment, it starts to become like a kind of stable. In between these two, you will see that it's more or less the same. What is telling us that the spread for the high flows values start to be much more difficult to forecast, and then it's not reliable a model after 3 4 time steps for the extremes. To do a more advanced way to analyze this data, then we can use, for example, LIME, local agnostic model explanations, and how they work. What you want to is just to fit a model with samples that have been perturbed to identify how these features are contributing. So in this case, for example, we took one sample. This is normalized sample, so that's minus 58, 0.58. And we started to make perturbations around the inputs that give this output, and then in QT between minus 0.4 to minus 0.49, in PT less than 0.37, and QT minus 1 between minus 0.44 and minus 49, and so on. The ones that you see on the left are contributing to bring the values of the output down. So every value that you put on QT, PT minus 2 and PT, QT minus 1 that is targeting this specific event will aim to reduce the values of the overall equation. And in which percentage? In this percentage, 28% of this contributes to 28% of the reduction of the machine learning model trying to reach minus 0.58. Same here, minus 0.37, any value in PT minus 2, all the values of PT minus 2 will reach 27% of contribution, trying to bring down the value of minus 58 inside the equation. So as you can see, this goes from the most important to the less important, yeah. And they are so close to each other that says that probably these features, the three features are doing more or less the same job. They are redundant probably, and they are highly correlated. But this is can only be obtained with this relatively detailed analysis, and this was only one sample. If I want to look to many samples, so to look at the whole model, then I should use Shapley adaptive explanation, or well, there are many more techniques, but this one is probably easy to think. So you compute a baseline of the model. So what is the current mean prediction of all the samples? Select a sample, and you can explain each one of the examples. And then for each one of the samples, you calculate the contribution to how much this was changing from that baseline. So if this is changing, it's like a kind of sensitivity analysis using game theory to give a weight. And then you at the end aggregate all the results in something like this. This is the graph that shows which one is the feature more important and the feature less important from top to down. And in each one of the feature, each one of these points is one of the samples that you have in your model. So I had 2000 data, so here 2000 samples, and then you can see how each one of these samples in the running the model contributes to the final feature, so higher or lower. So this is telling me already which ones are the variables that are more important, and inside those variables, some of the samples that I were using, how much they were contributing to bring the result to the right value or not. Now, what does give that message? Okay, it's relatively easy in terms of mathematical equation, difficult on our area of science because understanding and going through each one of these samples and explaining why one variable or other is giving more result, it's not straightforward. So wouldn't be more easy to start to say, okay, if I run the model with clear objectives and clear justification, maybe it's easier to understand the rationale. Even you can apply the same methods, lime and shape, but now under the assumption that if you had a clear justification and you clear build models, maybe you can relate. So some of the issues that sometimes we have is to find what is the importance of this questioning the need for the model. If you have a very good reason why to build your model, all the steps that I mentioned before and all the analysis will go relatively easy in the sense that you will avoid having problems like this one. So examples of redundant modeling. I have seen cases where there is a flood forecasting study in a region where never floods. Yeah, it's in fact going into more flow forecasting. Um, this maybe some people try to justify it, but because it's climate change and that area never have been floods, then now will be floods. But yeah, still is difficult because you are using a machine learning model and the machine learning model is based on the past. He doesn't know the future. So this type of game. Second is reproducing established formula. So I have seen this plenty of times. So if you have a formula that is being used and says, I will take in average precipitation, average temperature, average evapotranspiration, and I will say that it's a dry area, and then you calculate thousands of points with that formula, which is a very simple linear formula, and then you create a machine learning model to target the results of that formula. If you think about it well, what you are doing is only creating the formula, which was A plus B plus C, with thousands of values with a machine learning model. Of course, why to have thousands of parameters if at the end the real solution is just that formula? But there are many, many, many publications where at the end goes into trying to solve a problem that is not there. Copying physical models. And this is the surrogate case. Why to build a surrogate? Not always building a surrogate is necessary. If you have a physically based model and you want to analyze the scenarios where someone is going to remove an area of, you have a river basin and someone is going to make a deforestation, well, the machine learning model is straightforward, cannot do anything there. So keep your physically based models. It's not a matter of trying to put everything, uh, yeah, machine learning. Maybe you can find ways whereby the machine learning can aid the physically based or vice versa. But many cases, the surrogate is not justified by the fact that saying is faster. It's faster. There is no sense why you need to make it faster if at the end this is a design that will be done in a desk. It's not an operational forecasting where someone will die if you do not have the result on time. So it's kind of there are some deeper questions than just let's do the model. Drought replication formula, I was already talking about it. I have seen many people trying to estimate if that this is a dry area based on a formulation that if I have A plus B plus C, and then I say it's dry, then I build a machine learning model that will read A, B, and C to find if dry or not, then you're not doing too much. Um, so factors in the what is redundant modeling. So is no flood history, then you are going to attribute it to climate change or the other thing. Try to find a way that really makes us understand why you need the model. But not only that, later when you have the model, try to see if that model really is answering the question that you wanted it to do, because sometimes will not. How should I use the machine learning model to solve a problem with a known solution? Well, yeah, then maybe the reasoning is not to find the area that is dry or wet, but is try to identify maybe how complex are the variability of these parameters used in the equation, and maybe how much this equation at the end have probably certain elements that in the reality are not consequence. So you can find them probably rebuilding the machine learning modeling, finding where the machine learning model is not being able, or when the machine learning model is going certain direction and your equation was in another. Maybe that can give you some help. But it's not forcing the solution, it's just trying to understand where you want to go with it. And the third one is the idea of using these mimic and physical models, again, surrogates. So maybe having a surrogate can be used to integrate with other elements. However, they should be clear. Means this small physical element will interact with another, with another, and with another. Then, if I need to make all these interactions and I'm going to run the physical models, I will get crazy. Why not to try to make it with machine learning models? So that was the first part on terms of the uh, possible drawbacks in the models. The second part that I wanted to highlight here was the uh, common paradigms. And if you have been in a lecture on machine learning, you will see that this is very familiar for you. So maybe when you are doing feature engineering, yeah, half of the work can be done if you already know physics, you know the physics of your problem. So sometimes you might see that in a machine learning approach, some people might take, for example, all the hydrological variables, then they make the correlation analysis, and they find that temperature and precipitation is weak. But you, as a scientist in hydrology, you know that there are certain periods or certain moments where this temperature and precipitation are very, very important and dominate. So how you bring into the context the knowledge that you know that is not explicitly blindly using the machine learning model theory. Second one is over parameterization and versus small data sets. So don't use always the most complicated model. most of the small models are very powerful for little amount of data, and then also you risk less with this overfitting when you have known yeah elements. Next one is why feature learning analysis in deep learning, and this was in a in a workshop. It was interesting that if you guys want to do one day uh, a feature learning in a deep learning, then there seems to be a contradiction, because the deep learning, if you go to Wikipedia or the definition of the deep learning, is meant to learn the features. So you throw them all the features, convolutional neural, you put the whole image, you don't care about the features, you don't know the features, you let the machine learning model find the features for you, give them weights. The same LSTM. LSTM is not anymore like I was looking at the correlation 1, 2, 3 days. No, LSTM, you put them 365 days. You put all the features, and then he will give you weights on those features, and he will work with the whole thing. So it seems contradictory to keep the analysis of feature learning while the feature learning is now embedded into the deep learning process. Something to think about. uh, Space-time, rainfall, runoff, and this goes into the dynamics that many people say, okay, why I will include information from the neighboring basin, or why I would include this high resolution precipitation information if at the end I'm going to average it in the basin. That's quite true. However, if you characterize those patterns, they might provide you information that is not a straightforward physically based information, but those patterns might be proxies of what is happening in your basin. So knowing what is happening all around you will allow you to learn, or the machine learning to learn, how these properties of the surrounding environment are changing the properties of your current environment. So that's another important thing. So these challenges were in kind of machine learning past, but now in the present, recently, there are new paradigms coming. Well, the simple one is not so new as well. This is quite old. In fact, you are working with a time series of information from years, and the years have seasons, and then you have rainfall in summer and in winter. One question that someone might ask you is, what is more difficult to forecast, in summer or winter? And the answer is probably related to the type of phenomena that you are trying, and the region that you are forecasting. In fact, if it's in summer, it's more difficult to forecast, because the in summer is convective rainfall generated by evaporation, goes pretty fast. Are small areas, move quite fast, and then it's more difficult, more dynamic. Large cumulus rainfalls uh, well, are relatively easy, because it's a big mass moving in the atmosphere. Easy to track, easy to know more or less how there will be rain for sure. One of the ones that I most like, and there is a YouTuber that talks about physics, and she says that this paradigm is one of the most important things that has happened right now in this use of these large language models. It goes in contradiction that probably many people have failed the exam in machine learning by saying or making a mistake in the conception of overfitting or the description. But it seems now that the in the large language models, many experiments have shown that they can continue. It makes this overfitting part, where your validation test starts to get more error, and your training starts to go down. but many of these experiments have shown that they continue running, and one moment the training brings the validation again down. Then that's a changing paradigm. That's a change in way of thinking. Now it's the overfitting has indeed a moment where most of the people stop, but uh, for certain experiments you can try maybe later in your own cases and to see how much you could let it run, and to see in which moment, if it happens, that goes down again this validation. That's a big question. The next one is deep learning and spatiotemporal dynamics. So how now we are moving into having more space-time information. So having images and continuous of images is allowing us to build up patterns of high dimensional problems. And this is a very big opportunity. There are recently many papers aiming at making combinations of this. And I think this is a big opportunity of bringing things that go outside of the physics of the conventional way that we think on the rainfall runoff responses or the hydrological systems, but it's an opportunity, I believe, in machine learning. Well, then coming into the end, I was thinking looking ahead, integrating nature and technology. As you can see, most of the things that I was telling you are related to bringing the physics into the understanding of what's the problem that you are solving with the machine learning. And somehow, when you start to see the training, the analysis, and the results that you're obtaining, you will be able to explain much more if you are in the area. So this is the end. So I thought that close with a statement in Latin, post hoc ergo propter hoc, which means after this, therefore, because of this. That means not everything that you see that happened after is consequence of what happened before. This is cause effect, or the same as many people say, correlation is not causation. So thank you, and yeah, I open for questions.